let's say I have 3 chairs. I'll just make them like they'll just be blanks. 1, 2, and 3. 3 chairs, and I have 7 people. I'll call them people A, B, C, D, E. How many is that? That's 5. F, G. So we have 7 people, and what I want to know is how many different ways can these 7 people sit in these 3 chairs? Well, before anyone sits down, if we just pick a chair, let's arbitrary. These are just arbitrary labels for the chairs, but let's just start at the left with chair number 1. If no one is sitting down, how many different people could sit down in chair 1? Well, 7 people are standing up. No one is sitting in any of the chairs, so 7 different people could sit in chair 1. So there are 7 possibilities for chair 1. So one of those 7 possibilities is going to sit down in chair 1. So how many people are left to sit in chair 2? Well, 1 less than 7, right? 6 people are going to be left to sit in chair 2. And then, of course, if 2 people are already sitting down, how many people are left to sit in chair 3? Well, there's going to be 5 possibilities. So the way to think about it, for each of these possibilities, there are 6 possibilities in this chair and 5 possibilities in that chair for each of those 6. So you would multiply all of the possibilities. Hopefully that makes some sense. We'll try it out with some examples. So the total number of possibilities in this case is 7 times 6 times 5. And what is that? 6 times 5 is 30. 30 times 7, it equals 210. There's 210 possibilities. That's a lot of possibilities. Let's do a slightly smaller example. Let's say, we don't have to do people in chairs. Let's say we have cups. Yeah, sure. Let's say we have cups, and I'll do the cups in a different color. So this is 1 cup, cup 1, and then I have cup 2, and then I have 3 balls. I have a magenta ball, I have a brown ball, and I have a yellow ball. And I want to know how many different ways can I put these 3 balls into these 2 cups. Well, assuming that I haven't put any of the balls into any of the cups as yet, how many balls? Well, let's just start with cup 2. I just want to show you that you don't have to start the cup that happens to be labeled number 1 and it's sitting on the left. So if we haven't put any balls into any of the cups, how many can we put in cup 2? Well, there's 3 possibilities, right? And for each of those 3, then how many can we put into cup 1? Well, we would have put 1 into here, so there'll be 2 left to put into cup 2. So it'll be 3 times 2 possibilities, which is equal to 6. And let's see if we can draw them out with. Well, let me number these cups because it's going to be too difficult to keep switching colors. So let's say this is A, B, and C. I'm going to show you that there are 6 ways of putting these 3 cups into these 3 balls into these 2 cups. So it could be A in cup 1, B in cup 2. It could be B in cup 1, A in cup 2, right? You could just switch them, so we actually care which ball goes into what cup, not just, is a ball in a cup. It could be A with C, A in cup 1, C in cup 2. It could be C in cup 1, A in cup 2. And then finally, you could just have B and C. B in cup 1, C in cup 2. Or C in cup 1, B in cup 2. And notice that if we just cared which of the balls were picked, but we didn't care whether they were in cup 1 or cup 2, we could get rid of this bottom line, and there would be half as many ways to place them. But when we care where the balls are, right? We care whether they're in cup 1 or cup 2, or in this case, we care if they're in seat 1, 2, or 3. The ways in which we're ordering, we call these permutations. And up here, the way we would write this permutation, we would say, well, how many ways can we fit 7 people into 3 chairs if we care about what chair they're sitting in? So we could write that as 7 people, and the P isn't for people, it's for permutations, into 3 chairs. And another notation for it, you write a big P and you say, how many ways can I put 7 things into 3 spaces? Or it could be written as, how many ways could you put 7 things into 3 spaces? And in this case, we got the answer is 210. And actually, it will always be 210. And I'll show you why in a second. And how would we write this? Well, this would be, I'll do it in green because we had three things and we put it into two spaces. So three things into two spaces, and that's the same thing as three things into two spaces, which is equal to three things into two spaces. I'm just showing you the different notations, and we figured out that that was 6. Let's see if we can figure out a general formula if we wanted to evaluate, n, p, k. How many ways can we fit n things into k spaces, right? So if we think about it, we're going to have, let's just use some analogy. We'll have k spots. So it'll be, 1 spot, 2 spots, 3 spots, all the way to k spots, right? In the first spot, there's n possibilities, just like we did in the last two examples. There's n possibilities there. Then, since one person or one thing will be placed in spot 1, there's going to be n minus 1 possibilities for spot 2. And similarly, n minus 2 possibilities for spot 3. And then we could follow that pattern all the way. And how many possibilities are there going to be for spot k? Well, in everything, it's n minus 1 thing less than the spot number in our case. I mean, I guess we could have started with spot 0, but this is better because we actually numbered all the way to k. So it will be n minus k minus 1, right? And that might seem complicated, but it makes sense. Like when we did, 7 things into three spots, we went 7 times 6 times, we literally put in the top 3 of, you could almost say from the factorial, right? 7 factorial would be 7 times 6 times 5. I think this will help it. If this was just 3, it was 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 7 factorial. But we only took the first 3 of the factorial. And similarly, 6, well, 6 is also 3 factorial, but another way you could view it is we only took the first 2 of 3 factorial. So what we're saying here is we just take the first k of n factorial. So is there any easy way to write that? To write the first k of n factorial. Well, sure. We could write it as n factorial, and the formula is almost harder than what it's saying. We could write it as n factorial, with a lowercase n factorial, over n minus k factorial. Let's see if that works. Well, what's going to happen? So in this case, n factorial was 7, so it was 7 times 6 times 5 times 4 times 3 times 2 times 1. And then what was n minus k factorial? Well, in our example, k was a number of spots, and there were 3 spots. So 7 minus 3 is 4. So 4 factorial. So it's 4 times 3 times 2 times 1. And of course, this will cancel. Let me do that in a different color. This will cancel with this. And so you're just left with the first 3 of 7 factorial, or the 3 largest components of 7 factorial. I always rederive this because all I think of is what we did originally. I was like, oh, okay, if we're doing permutations, the first spot, I just start the factorial until I run out of spots. So I do 7 times 6 times 5. And let's see if it works out here too. So what is 3 factorial, because we have 3 different things, 3 factorial over, and then 3 minus 2 factorial, right? 3 minus 2 factorial. Well, that's just 1 factorial, right? So it becomes 3 times 2 times 1 over 1. And of course, the 1's cancel out, and we got the 3 times 2. Hopefully that makes sense. A lot of people, they learn the permutation notation, and they say, oh, that's n factorial over n minus k factorial, where n is the number of things I need to place, and k, n minus the whole thing factorial. And k is the number of spots I have, and they just memorize it. But all this is saying is you start, almost just, multiply, doing the n factorial, but you only do the first 3 components of the factorial. And it makes sense just from how we started off the video. If you have 7 things, well, 7 things could go here, 6 things could go here, 5 things could go here. No more spots, just multiply them. And that's all this formula is saying. Hopefully I didn't confuse you, and I will see you in the next video on combinations.